Welcome to the third part of the lectures, SemiFree Resolution and Application. So today we are moving straight to the application of the SemiFree Resolution through the Allen-Bemore differential tau. Before we go ahead, let me remind you what we did yesterday, the main results that we obtained yesterday. So yesterday, we defined the Allen-Bemore tau of Mn as the homology of P with where Pm here is a right semi-free resolution of M. Okay. Yesterday we also see that we also saw that if M prime, if M and M prime are two A module, let's say A modules with respective resolution then we have P we have this map. Here we have the identity of P tensor P n P J prime tensor T n. Here Tn here is, I define this map A tensor B to B tensor A. The map A T A B is just the map who interchange the position of A and B as follow: -1 degree of A, degree of B, B tensor A. This is what I did. I did this the first day. So using this map, we have a relation between and prime here so with this map we have a relation between the tensor product of two Allen-Bemore tau with the tau of the tensor product. We have this relation here. Let's call this map phi. Okay. Now the third result that we saw yesterday is that if phi is a map, algebra map from A to A prime, M is a map beta M prime and N prime are A prime module, M and N are A module, then we have so yesterday. We also saw yesterday that I'm just trying to remind what we did yesterday, so that you should have it in the mind before going on. That if I have A, B, C, and D here, P1, phi 2, phi 3, and phi 4 here, A1, A2, A1, B1, C1, T1. Here we have alpha 1, alpha 2, alpha 3 here, and alpha 4 here. We have here A2, B2, C2, D2, alpha 2 here, beta 1, beta 2 here, beta 3, beta 4 here, and beta 3 here. Then if these three maps are commutative up to homotopy, then we have this commutative diagram. This commutative diagram have here the tau of A1, A2, tau of B, B1, B2, tau of C, C1, C2, and next we have here the tau of G, D1, D2. Here we have the maps tau of phi 4, alpha 4, beta 4, tau of phi 1, alpha 1, beta 1, and then you have here the tau of phi 2, alpha 2, beta 2, tau of phi 3, alpha 3, beta 3. This diagram is commutative. We saw it yesterday. Okay. Now that I have reminded all these results, let us move to the next part. That is part 3. Okay. Let X be a topological space. We saw that the normalized singular quotient is related to the singular quotient by this map. We saw it when we were doing the notion of singular homology and cohomology. We saw it. So this map is, I told you that this map is a quasi-isomorphism. Let me call this map theta. Theta is a quasi-isomorphism. Means that in homology theta is an isomorphism. So by using this map, we have this relation it will be better that I should write it vertically. Okay. How can I get this homomorphism? I get it from this map, because what we have is if the normalized singular quotient is related to the singular quotient, then we have the opposite algebra, which is also related to the enveloping algebra is also related to the enveloping algebra in this side. So this map is transferred to this by taking the enveloping algebra. Let me call this phi. Okay. Now we have this relation. Let me call this map alpha. So by applying the relation phi alpha beta that I defined before, we have here the term of phi alpha and alpha here. This is what we have here. Since alpha is a quasi-isomorphism, phi also is a quasi-isomorphism, this is an isomorphism. Because this map, I told you that this map is this map, I called it theta. Let me change it by theta, but I called it theta. It's theta. I told you that this map is a quasi-isomorphism, means that in homology you have this. So by moving to the Tor, you have this as isomorphism. Okay. This is one of the results. Let me call this result A. Okay. Proposition. Let X be a topological space, and X the normalized singular quotient. I will denote the normalized singular quotient like this. Normally, the normal notation is this one, but what I will use is this restriction notation. Okay. So X is a topological space. The normalized singular quotient is this. We have this composition here. Let me write it vertically. It is better to obtain it vertically. X tensor and X. And here we have n X tensor and X. Here we have the quotient complex, and here we have the normalized chain complex. So we have, by taking the dual here, this is the dual of this coalgebra. We have a map which moves from this to that, and then we have here okay. So this composite here, I called it nu. So nu here is equal to the composite by I. This is the Alexander-Whitney map that I defined yesterday when I was doing I was defining the structure of algebra and algebra on the normalized singular quotient. I defined this map. Okay. So this map, I told you that this map is an equivalence. So by moving to the homology, we have an isomorphism to this map. So and here we have the first thing that I define here is this one. And the other one is here. Okay. So the identity is a map from the normalized singular quotient to itself. The same identity, you have it here. We have the map nu from this tensor product to the normalized singular quotient of the Cartesian product of x and x. So with these three maps, we define the relation between this Eilenberg motor and this other one. What I claim here that this map is an isomorphism. Let us prove it. So what we are going to prove here, we are going to prove that the identity is a map of nx to nx as the nx cross nx module to n of x cross nx. That's what I want to prove. If I have, let's have here like this. We have a k vector space, B a k prime vector space. We have here F a linear map from A to B, means that f of alpha x is equal to phi of alpha f of x. This exactly I'm doing. This is what I'm doing here exactly. Okay. So let us define the action of nx on this. Okay. So the action is given with this relation. X here, let me call this A, X. We apply A to X. I'm calling this action, I'm denoting that as this action by this side. So this is by definition equal to something which is not correct here. Okay. Delta x here is the usual topological diagonal. That is, the map delta x here is a map from x to x cross x, which assigned to any x, x, x. So when you consider our A here in this tensor product, by this map we obtain something here. So since nx, n is a covariant functor, so which this map this functor permit the domain and the codomain here. So we have delta cross delta of n delta of x I'm saying that n is a covariant functor. That means it permutes the domain and the codomain through this map. So what we have here is exactly n of delta x here. That's what this L then delta is come from here. We applied it to this, to the new, and then we take the crop product with x. This is the first action. The next actions is the action of tensor product with x to as follow. N cross x tensor n x nx like this, send it to nx. This set act to nx on the right side as follow. Consider x here and here b. let me denote this action like this. Okay. We have x is equal to what? Is equal to x copt n delta x of nu of b. This is the action of this tensor product on nx on the right side. Here we define the action on the left side. Okay. We are also going to define the action of n x cross x on nx on the left side. By this, n x cross x act on n x, the left side, yes, as follow. Let me denote it by star. Consider here z, and we consider an element on the normalized angular quotient x. Z act on x by, we take the coproduct of x n delta x of our A. Yes. Okay, now the action of this normalized angular quotient on the right side. On the right side, we denote it by star bar. So we consider here A an element of the normalized angular quotient, and an element here, we call it Z, and we have the action of Z on A on the right side, given by x. Here we have x. The first one is this one. The first one, this is the left action, yes. There's a mistake here, please. Nx delta x applied to A copt to Z copt x, and here we have x copt n x delta x applied to our Z. Have this. Okay, so with this action, we can verify that the identity, the two maps here, are a map of so means that if we have the action here, if we consider something here, A, then we have the identity of an X on this, we have the identity of A, the action of this. Is equal to A X. This is what we are expected to have. We are expected to have this relation. Means that the identity of this equal to this, and equal to X. We are expected to have these two things. So saying that this map is a nx cross nx module means that we have exactly this. It is what I told you before. I told you that if A and B are this one K module and this other one is a K prime module, you have here a map from K to K prime. Then we have F alpha A for some alpha. Consider taking here, we have this equal to phi of alpha f of A. This was exactly what we are trying to do here. Okay, so how can we verify this? We'll verify this by this relation. We have A for all A in N tensor Nx tensor Nx. We have, and for all X in Nx, we have A applied to X. This is the first action. Is equal to nu of A star X. This is exactly the identity of A applied to this, which is equal to the nu of A star the identity of X. The identity, the nu here was the map from Nx cross Nx to Nx X. So this is for the left side. For the right side, we have A, the right side, equal to X. So also this is exactly equivalent to the identity of X A here equal to X star bar nu of A. Means that the identity are exactly a map of Nx tensor Nx, Nx of N of X cross X module. So with this, remember that I told you that if A and A prime are two algebra, M prime, N prime, M and N are A module, M prime and N prime are A prime module. Then we have isomorphism phi alpha beta from tau of A n no m n to tau of A prime m prime n prime. This is exactly what we are doing here. Our phi here is nu from nx tensor nx to nx cross nx. Our alpha and beta are the identity map I defined here. So we have here tau of nu of the identity have here and here we have here the map nu here, and here we have the identity and the identity here. It's okay. So the map that I was supposed to construct is this one. So since this is an isomorphism, this is an isomorphism, this is also an isomorphism. So the map, this map is an isomorphism according to the proposition that I gave you before. Okay. Now let us move to the notion of Hochschild homology. We are going to define the notion of Hochschild complex with a general algebra, a differential graduated algebra. But to apply it to the notion of semi-free resolution, we'll use a topological space. So we will use the normalized angular quotient as algebra. Okay, so let us start with the notion of bar construction. Hochschild homology. Hochschild homology, Hochschild complex, bar construction, and cobar construction. These two notions are functors. The bar construction is a functor from the differential graduated algebra category to the differential graduated coalgebra category, which assign to any arrow here the arrow in the category of, let me take A prime, in the category of coalgebra. But there are many kind of bar construction. I will start with the general one, and then we'll move to the particular case gradually. So bar construction let A, D, A, B, A, graded differential graded algebra. That means our A here is equal to AI, I greater or equal to 0. D here is the differential from AI to AI plus 1. This is for all I. And we have the product MA defined from A tensor A applied to index n, which is equal to A to the summation of AI tensor A j, A plus j, I plus j equal to n to MA to AN. And we have the following short exact sequence 0. We assume of course that our A is augmented, so we have the augmentation here. So we have the following short exact sequence. And here we have this okay, and here we have K here, okay, 0 here. Here I have the augmentation, and here we have the inclusion, where I is equal to the kernel of epsilon. Okay. Okay. Of course, now that I have to define the notion of bar construction, I am supposing that you have the knowledge on the tensor algebra and the co-algebra on on the tensor product. Means that if V is a differential graded module, TV is just a summation of T, K, V, which K greater or equal to 0, or K from 0 to infinity, with T, K, V equal to what? Equal to V tensor V tensor V K times. There is an algebra structure here defined by what? TV tensor TV is exactly this. It's just a concatenation of the two terms. If you consider here a generic element here, x1 tensor x2 tensor xk, and y1 tensor y2 tensor y3 tensor yk, to multiply this by this one is just to concatenate these two elements. Means the product will give us xk tensor y1 tensor y, let's say of this, just a concatenation of these two elements. And the coproduct here is just, if you have x1, x2, xk, the coproduct here is just the summation of x1 tensor x2 tensor xi tensor xi plus 1 tensor xk I from 1 to k. This is the coproduct defined here. So when you have a differential guided module, you can take the tensor product on this differential guided module, and you have, it is defined like this, you have the product on this tensor product, which assigned to this tensor product the structure of algebra, and you have the coproduct, which is denoted by this, which is assigned to this set the structure of coalgebra. So having this, keeping this in the mind, we define the bar construction of the normalized bar construction, because they are the unnormalized bar construction. The normalized bar construction is what? With coefficient m and n. The normalized bar construction of A with coefficient m and n. This is a coalgebra, because I told you that B is a functor from the category of the algebra to the category of coalgebra. So this coalgebra is defined like this. M tensor n tensor so that for all k, bk of m n is equal to what? Is equal to m tensor a generator here, because this is a free module, a generator here has the form m, let me take it, tensor SA1 tensor SA2 tensor SAK tensor n, where remember at the beginning I say a word on the suspension of degree. SV I equal to S equal to V negative 1 and SV I equal to Vi plus 1. I say a word on the suspension of degree. So our S here is the suspension of the degree. Okay. This element is usually denoted by A1, A2, AK, and M here. So a generic element in this is exactly denoted by this. Okay. Now we have the differential here. The differential here is defined by n. Okay, the differential is given by what? we have here d is equal to d1 plus d2. Okay, where d1 apply to m, d1 is defined from b, k, m, n to b, k, m, n, such that d1 of m, a1, a2, ak, m is equal to what? Is equal to dn applied dm applied to this element here, because m itself is a differential A module. You applied it to m. Then you have here a1, a2 up to ak, n plus summation I from 1 to k negative 1 power epsilon I m a1 a2 d a applied to ai ak m plus the last term negative 1 applied to power epsilon k plus 1 m a1 a2 a k d n applied to n. This is our d1. Okay. Definition of d1 and the definition of d2. The d2 reduce the length of the words. d2 is defined from b, k, m, a, n to b, k, negative 1, m, a, n by d2 of m, a1, a2, ak, m here is equal to what? Is equal to, alors, is equal to a, you have here a m, a1, and then you have a2, a3 up to ak, m plus summation negative 1 power epsilon I from 1 to k, m, a1, a2, ai, negative 1, ai plus 1, ak, have n here, and the last plus the last term is given by negative 1 epsilon k plus 1 m a1 a2 up to a k negative 1 a k dot n. So the two differential are there, and if we denote this generic element, if I denote it by, let's say, u. So the degree of u is given by the degree of m plus degree of n plus summation of degree of ai negative k, I from 1 to n. Because the suspension of ai is exactly the degree of I negative 1. Degree of the suspension is given by this. That's why we have this last relation here. Okay. Now that the bar construction with coefficient has been defined, we can define the bar construction with coefficient on the right side and on the left side. When m remark, if m is equal to k, then b k a n is exactly b a n, which is the bar construction with coefficient on the right side. In the similar way, we have when n is equal to k, this is a bar construction of A with the coefficient on the left side. And finally, if m equal k equal n, b k a k is just denoted by and called the reduce normalized bar construction of A. Okay. And of course, the differential here and here can be reduced from the differential that I gave you before. So now that we know what is the bar construction, let us define the co-bar construction. But before the definition of the co-bar construction, there is another important remark, which tells us that the bar construction of A is a semi-free resolution over which is equal to, I defined it over the enveloping algebra. Okay. So So the differential Eilenberg motor of A over the enveloping algebra is exactly this, according to the definition of the thought that I gave you. Now, the cobalt construction is what? The cobalt construction is just the adjoint functor of the bar construction, defined from the category of differential graduate coalgebra to the category of differential graduate algebra. Differential graduate algebra, okay, which assigned to any coalgebra here, image, and omega C is exactly what is the tensor product of C, which is equal to so omega k here, C is equal to T k of our C. A generic element here denoted is of the form has the form C1 tensor S negative 1, C2 tensor S negative 1, C K, habitually denoted by C1, C2, CK. Voilà. Okay. I said before that omega, the bar construction and the cobar construction are adjoint functor, means that here I have the cobar construction functor, here I have the bar construction. So the fact that the two are adjoint functor is just is traduced by this relation for all A object of differential graduate category, differential graduate algebra category. We have omega B A isomorphic to this is a set of algebra homomorphism from omega BA to A, and this is a set of coalgebra homomorphism from BA to BA, from the bar construction of A to itself. Okay. So remark that here we have the identity map, the identity of BA. Through this bijection, there is a map here which is a correspondence of this map. Let us call it alpha A. If I denote this bijection by omega, or let's say omega bar, alpha the omega bar of alpha A is equal to the identity of BA. Okay. So there exists a differential graduate algebra homomorphism from omega BA to A, so that the range of alpha A by omega bar is equal to the identity. More precisely, alpha A defined from omega BA to A is defined by A1, A2, up to AK here. We send it to alpha A of A1 of A1, A2 up to AK equal to is equal to 0 if K is greater than 0, equal to A if K is equal to 1, equal to if K is equal to 0, we have here, we have just here 1. Okay. Alpha A is surjective quasi-isomorphism. Isomorphism means that there exists IA from A to omega BA such that alpha IA composite by alpha A is homotopic to the identity of omega BA, and alpha A composite by EA equal to the identity of A. Okay. So with this relation, we can go directly to the definition of the Hochschild complex. A Hochschild complex is Hochschild complex. It's just the differential graded module such that for all K and the differential G here is given by GA tensor B plus D0 negative D1. D1 and D0 has been defined in the note. Okay. You have D0, D0 has been defined here, and D1 is defined here. So, when we have a differential graded module, you can compute the homology of that differential graded module and obtain what we call the Hochschild homology of A with coefficient in itself. Have this. Now, so the Hochschild homology of A with coefficient in itself is just the homology of this complex here. Of course, an element of a generic element of CK X belonging to CK A is just is of the form X equal to A, that's called E0, A1, A2 up to AK. Okay. And when we replace A by the normalized angular quotient, which is an algebra we obtain the Hochschild complex of nx with coefficient in nx, and the associated homology is the Hochschild homology of nx with coefficient in nx, generally denoted by x. So when A is replaced by the normalized angular quotient, the Hochschild complex become this, and the associated Hochschild homology is given by this. The star is down, it's not up. Okay. Given by this. Okay. Now let us go to the relation between. Let us define the structure, the algebra structure on the Hochschild homology. So to define the algebra structure on the Hochschild homology, we need the strongly homotopy commutative algebra structure on A. So strongly homotopy algebra structure. Okay. The strongly homotopy algebra structure has been introduced by Moncourt. But we are given here another definition which is related, which is equivalent to the one given by Moncourt. So we say that an algebra, a differential algebra A, D, E, has a strongly homotopy algebra structure if there exists a coalgebra map denoted MB from BA tensor BA to BA, satisfying some properties. The properties are there. Strongly homotopy commutative algebra. Okay, we have it here. The property, let me give you the property. Bar construction. Okay, let me give you properties. I give you the property is this one. If denoted by P1, P1 is just the projection to then we have these properties. We have P1 composite by MB applied to what? Applied to A1, A2 up to AK is equal to P1 applied to B, MBA applied to A1, A2, AK. Here, this term is just correspond just to the case when you have the zero tensor product of A. Means that we are is equal exactly to K. Okay, this is the property related to that structure. Now, when you have let A and A prime be two algebra, partial granted algebra, then our objective is to combine this, to transform this tensor product of bar construction of A and A prime respectively to the bar construction of A and of A tensor A prime. This will be done by using a map called the shuffle map. The shuffle map is defined from this to that as follows. A1, A2, up to AK, tensor up to AP, tensor B1, B2, up to BQ equal to summation of what? Summation of epsilon sigma here, sigma, C1, CI1, CI2, CI P plus Q here. The sum is running on the cyclic permutation such that 1, 2, Q and Q plus 1, Q plus 1, Q plus 2, Q plus Q appear in this term appear exactly in this order. Means that we consider all the permutation where we have this order, this 1, 2, 3 up to P appear in this order and the other one appear in this order, something like this. Let us take 1 P equal to 2 and Q equal to 3. Then you have P plus Q equal to 5. We consider the permutation of this form 1. Have the permutation 1, and then you have let us take here 3, 2, 4 and 5. Okay, this is a permutation 1, 2, 3, 4, 5 here. 1, 2, 3, 4, 5. Okay, so 1 and 2 appear in this permutation in this order. So we have 1, 2 are ordered in this order, and then you have 3, 4, 5 also appear in this order. This is an example of the permutation satisfying to this condition that I said before. Okay, now that we have this, we have the shuffle. The objective of the shuffle is to combine to transform the tensor product of the bar construction of A and A prime respectively to the bar construction of the tensor product of A prime. So by using this, we are going to define a product on the Hochschild homology as follows. Okay, we have here A, G, a strongly homotopy commutative algebra, strongly homotopy commutative algebra with the structure of homotopy commutative algebra given by mu. Mu here is related to our MB that I defined before by this relation. Let me give you that relation. So mu here is equal to this relation alpha A composite by omega nu A, where nu A here is just the map defined from B A tensor A to A. Okay. So I told you that MBA is a map from BA tensor BA to BA. That's what I told you. So from the fact that and from this we have this map, have here SH, the shuffle map. Our nu is here. Okay. So our mu A is equal to what? Is equal to alpha A composite by omega of MBA composite by psi A, where psi A is just a map from omega B from BA tensor A to omega BA tensor BA. Okay, psi A. Okay. So our mu is alpha is a quasi-isomorphism, psi is a quasi-isomorphism. So we have this relation, this relation between this mu and MB is the one establishing the relation between the strongly homotopy commutative algebra given by Moncourt and the one that we define here. So the strongly homotopy commutative algebra we define is this one, and the one defined by Moncourt is this one. The two are related by this. So using this, we have we have this, and then we have this. This is shuffle map, and then we have this. And this is SAA, and then we have the last one. This is the Shuffle map. This is the SEA. This is the CAA. Something which is not correct here. Okay. Okay. So this composite here, okay, is let me denote it by phi. And clarified, of course, the shuffle here, shuffle defined from A tensor A. This is the shuffle that I defined. The shuffle when you want to move from the tensor product from the tensor product of two chain complex to the chain complex of the tensor product. I defined it here. This is the, you have, I told you that omega BA, omega BA, that this map is a quasi-isomorphism. So we have the inverse of this map here. So at the level of the chain complex, you have a quasi-isomorphism from omega B A tensor A to A tensor A. Let me call it this. You have the inverse here, and by putting the Hochschild complex here, functor here, we have this relation. So this is also a quasi-isomorphism. And then mu here is the map of the strongly homotopy commutative algebra here. So finally, we have phi equal to C mu A composite by S A composite by S H, the Shuffle map. Okay. Now I'm going to the homology. We have, which is defined from the homology of this tensor product to the homology of phi is defined here. But what we want to have is the map from this is what we want to have. So how to move from here to here? We use the kinet isomorphism because we are working on the field. It's an isomorphism. So finally, the product we have is, we call this isomorphism, call it tau. The product on the Hochschild homology of A with coefficient A is just of phi composite by tau. Okay, there's some points which are not very clear because this is the section of a quasi-isomorphism. This section is not unique. But when we move to the homology, we have the uniqueness because all the sections are equivalent. To the homology, they are equal. So the problem of the uniqueness is resolved here. Okay. So now we have the product on the Hochschild algebra, the Hochschild homology, that make this graduate module an algebra. And then we also have conclusion. C'est ça. Okay. Now I told you that BA is a semi-free resolution as AE module. We are going to relate the notion of the Hochschild homology to the Tor differential, to the differential Tor. Link between the Hochschild homology and the differential Tor. Okay. Okay. What we have here as link is that the Hochschild homology of A with coefficient in A is isomorphic as algebra to AA, as algebra. This comes from the fact that this is a semi-free resolution. The proof is done here. Okay. Je n'arrive pas à gérer ça. Ok. This is the proof of the fact that the homology algebra is the Hochschild homology is an algebra. The proof is here. Now we have the connection with the Allen-Bay motor here. So the relation between the two is here. So by using this relation, if we move to, we assume that our A is equal to nx, then we have the relation between the homology of okay. Let me summarize what I did up to now. I was trying to I have established that we have this relation firstly, and we also have the link between nx, tensor nx, isomorphic to tor of nx plus nx. Okay. We also established that tor of nx this is an isomorphism as vector space. Okay. Now we are going to establish that so at the end we have the relation between this and that, we have relation between this and that, we have relation between this and that. So it is necessary for us to have relation between this and that relation we have it because I told you that we have tor of nx of nx isomorphic to tor of cx and cx So we have also this relation. So we are going to have a link between this one and this one, and then have a link between this one and this one, so that these two things should be isomorphic as algebra. Before we go to the end of the class, let me explain more this relation here. We know that our complex is equal to this, and you also know that is defined as, have here A so we will try to build a bijection from this to we call this bijection theta. At each degree for all k belonging to n, we have A. Here, let's say, let me call it I. A generic element here is of the form A1, A2 up to AI. We send it to A, tensor 1, A, A1, AI. And this map here is a bijection which the inverse So the map defined here, at each degree we have this map. The restriction of this map is defined like this, and the inverse of this map is exactly this. We can compute easily that theta I composite by theta tilde I is equal to the identity, and theta I tilde composite by theta is equal to the identity. So there is a bijection between these. The left side is exactly is the Hochschild chain complex, and the left side, the right side, sorry, is the one defining this. So by taking the homology here and the homology here, we have the homology, the Hochschild homology. The homology of on the right side we have this, and this map is a bijection, means that we have here a bijection, but we need to have to show that this bijection is compatible with the product. What I will do here is to define a product here, and then, because when you have a bijection between two sets, if there is an algebra structure here, that algebra structure will be transferred here via this bijection. We can build a bijection in B, BA, tensor A, like this. Alors, let me because the construction of that product is okay. have here A, B, A, A. We transform it by itself, A, like this. When we go to the A, tensor BA, tensor by, let me go directly to BA, A. This product is exactly what? Is exactly M A tensor nu A, tensor M A, composite by what? Composite by the okay. All the maps appearing on this composition has been defined before. So we have the product from the product of the tensor on the bar construction of A with double coefficient A and A prime and A. Sorry. So having this, you have A is an algebra with the product MA. BA A is also an algebra. So taking A, we have the structure of algebra here. So the isomorphism that I constructed here can be transferred to this one via the bisection that I construct. That's why we have this as algebra. And when A is equal to the normalized angular quotient, we move to the topological relation. Okay, so we have this. So I was saying, as I was saying before, tomorrow we'll end with these lectures by establishing that the free loop space homology is related to the Eilenberg-Moore differential tau, and then we'll build an algebra structure between the two Eilenberg-Moore Eilenberg-Moore differential tau as an algebra. The part that I was supposed to expose today is finished. So I still available to answer to all questions that can be asked by the participant.